get at least one of that specific event come to mind. And it's a lot harder to understand and grasp based off of your scenario at hand. We'll also be focusing on a conditional probability, which, just as the word entitles, it means we're looking for probabilities under these specific conditions. And it kind of relates back to the previous section when we're looking at the basics of the multiplication rule. So we'll be looking at these two specific scenarios for this section. And like I said, it's really a matter of the keywords and understanding these phrases. So what we'll do now is we'll work on a problem with the complements or the at least one scenario. And we'll look at one. We will not approach it with this at least one approach. We'll just tackle it head on and see like the main difference why we want to utilize this at least one technique. So we'll go to the next one. And this leads to our first example, and that is the type of, this should be question 1 for us. Whoops, question 1. Okay, so it's asking us to find the probability of a couple having at least one girl among 3 children. Assume the boys and girls are equally likely and that the gender of a child is independent of any other child. So before I just introduce this at least one technique, let's actually go through and see what this means or entitles us. And the whole idea is when we look at this at least one. Forgive my handwriting, please, but. So if we want at least one girl. And a lot of times, like the best scenario I use for my class is, let's consider the instance when you are an adult. So you are considered an adult when you are at least 18. And what that really means when you are 18 or more. So the at least does not mean less than the number. It is the opposite. It means you are looking for that case or when you are more than that. So on the next slide, we're just going to go through this critical thinking. So no matter what, look at the sample space. And in a previous section, I actually drew and taught you how to get the sample space with the tree diagram. So these are all the possible cases or outcomes when we can get the birth order of a couple wanting three kids. And remember, what we want to tackle here is we want to get at least one girl among the 3 children. So at least one, it really means I'm looking for the probability of getting the one girl or getting 2 girls or 3 girls in this. And that's the one downside. Because I'm looking at this scenario where I want the probability of 1 or more than that, it turns into an or statement, which means I need to find the probability of each specific scenarios. So from here, if I go back to my setup, I want my tool. So I'm going to move this with the mouse so I don't mess up my recordings. There we go. So from here, this is what we need to remember. Whenever you have that at least one case, it means you are getting 1, 2, or 3 girls in this. So what that really entitles us is the at least statement. At least one, it really means we need to get 1 or more of our specific case. And remember, we focus on this or statement at one point as well. When you have the or statement, what that entitles us is we are using the addition rule. So this or statement, it signifies we use an addition rule to add all the probabilities together. Okay, now depending on the situation, it could be a straightforward addition. It may be a long, tedious addition rule. For this problem here, at least one girl means we want to get the probability of 1 girl, 2 girls, or 3 girls. So if I look at the sample space, I can find that. I'm going to look for each event from here. So the probability of the one girl, there are 8 total outcomes from here, but if I want just one girl, I have to count from here. So I have one girl here. I have one girl here as well. This is 2, doesn't count. Here's the other case where I have one girl. So for this one, there are 3 cases of getting the one girl. So our probability to get the one girl is the total number divided by the sample outcomes here, which is 8. Okay. Now, if I continue this again, if I want to find the probability of getting 2 girls from here, I'll use a different color. I'll let 2 be in blue. Once again, I want to count. So I need to get 2 girls from here. And I see one here. 2 girls right here. And I have 3 again. So probability of 2 girls coming up would be 3 cases out of 8 total. And now let's look at the last case. I'm going to do that in red. I want the probability of getting the 3 girls. And from here, there's only one option for this. It is the final one. So to get the 3 girls, it is 1 out of the total. Okay, so I have all of these possible cases here. And what I do now with the addition rule is I have to add up all of these probabilities together. So if I want to find the probability of getting at least 1 girl, which I'll put as a G, I'm looking at the probability of 1 girl plus probability of 2 girls, and then probability of the 3 girls appearing, which I found all of those right here on the side. So this is really 3/8 plus the 3/8 again, plus the 1/8. And I just add up the numerators together, which would give me 7 divided by 8. And that is our probability of having at least 1 girl from the 3 children for this couple. So that's our probability here. Now, I did this on this side because I realized I made a mistake. The numbers did not add up. So this is supposed to be the 3. This is supposed to be 3 as well. So that was my fault. But from here, I still end up with the same probability. So the probability of getting 1 girl from among the 3 children, it is 7/8 from here. Now, this was us just tackling it head on. This was a reasonable problem to perform this tedious task. But let's say we were looking for at least 1 girl among, let's say, 10 children. If it was for among 10 children, that means I need to find at least 1 girl from that larger sample. And I may not have my sample space right here, so I would have to construct it with a tree diagram. And that tree diagram would get a little bit intense when we kind of branch off all the values. So that is one of the disadvantages to this aspect. If I tackle it head on, I may have so many outcomes, I have to keep track of all of them. We may have to perform this at least statement, not just up to 3 children. Let's say we would have to go up to at least 10 of them at one point. So there are some downfalls with this technique. So this is the main approach what we're actually looking at. When we look at this at least statement, we are really going through the aspect of all these multiple scenarios to where it is not specifically set to one event. It could be the multiple events, just like this problem. So the reason I wanted to show you this is because there are some that are pretty straightforward, but in times you don't get that. And that's where this at least one statement or the technique for this approach comes from. It's a matter of condensing this work here. Because this is a reasonable problem, yes, but it's not realistic. I wouldn't really want to do this for like the 10 children and then repeat that for maybe 20 or 50 children if possible. So the at least setup, it's really us focusing on this aspect. Rather than looking at every possible outcome, let's take the complements and try and use those shortcuts to help us shorten this process and technique. So if I kind of observe on this, all the outcomes that I picked were from the sample space. But if I notice on this, I used all of these outcomes except for one scenario. The only one I did not use was this case. And if you look at this case here, this specific scenario, it omits ever having a girl. So all these outcomes that I had with the girl appearing at least once, I always counted it in the probability. But if I look in this very first case, there is a scenario where I don't have girls, period. And this is the beauty of the complement rule. What we're going to do is, rather than take this straightforward for every possibility, we're going to just look at the opposite case. When we look at the opposite case, we are able to shorten our work and just use our knowledge and the rules of complements to help us find the answers quickly. So we're going to tackle this problem a different way. We're going to look at the next slide, which helps us go through the same technique to find the probability, but we're going to use it with complements now. So for this one, I'm still tackling the same problem. I have my sample space once again, but the main thing we want to focus on is there an easier way? Well, there is. If we went back to the other side, we counted all the probabilities or all the outcomes where a girl came up. We're going to now focus on the single event where there were no girls. So this is the no girls section. Kind of sounds like Little Rascals at this point. So this was a one case where we had no girls appear. So we're going to look at that case. So we are going to look at this scenario. So that one outcome where I have nothing but, or I had just boys appear, that is the probability of no girls. Which again, it will just translate. There are some cases where it's best to translate it in the sense of what you have in this problem. So if I'm looking at no girls, that is equivalent to saying the 3 Berts were all boys. So we have all 3 boys. Okay. Now from here, what is this setup? What is the probability of getting this case? Well, I know from here, it appeared just once out of 8 possible outcomes. So this probability is 1/8. Okay. Now, this is a complement. I have taken the opposite of what we are trying to find from the problem, which was at least the one girl. So this right here we did, this is the complement of the at least one girl. All right. So this does not translate to what I want to find. We just found the complement of this one probability, but it's not the problem we wish to find here. So if I'm still focusing on complements, I'm looking at the probability of getting at least the one girl. And I need the complement of what I've just found here. And actually, I'm going to write that down rather than this. I'm going to put, if I want to get at least one girl, it is the 1 minus the probability of getting no girls, which we found. The no girls was that one case where you had nothing but 3 boys emerge from these births. So it's 1 minus the 1/8 that we had just found. Which if I subtract that, that is going to be equal to these 7/8. Now that is the exact same probability that we found when we did this technique in the tedious form, when we actually listed all the cases of getting 1 girl.